Right? Multi-share. So
Oh, okay. Okay. It's begin recording now.
good morning, good afternoon. It is my great pleasure to introduce our first speaker for this session, Professor Jiming Lee from Northwest University in China. The title of his talk is Ergodic Optimization for Random Dynamical Systems. Yes, you can get it.
Okay. Okay. First, thanks all of you. I have a chance to show my recent result to you all. And my title is Ergodic Optimization for Random Dynamical Systems. My, my talk has three parts. The first is motivation, and we will reveal some main results of our present work. And the last section is the further problems we're considering. Now, the setting of this this talk is very easy. We consider a compact metric space, continuous dynamical systems, and a function on this set, usually real valued or complex valued. Now we take all the Borel T-invariant measures. We look the supreme of the integral of the potentials with respect to all the T-invariant measures. So since this functional is continuous, thus there should be some measure obtain this supreme. We denote this set by Mmax. We call it the phi maximizing measures. Clearly, this set is non-empty. So for consider such ergodic optimization, we need to describe the complexity of the set of maximizing measures. So how to describe this complexity of this set? We have two approach. The first approach is by adding additional hypotheses on the dynamics of T or the regularity of the potentials. In 2006, Jackson obtained the first result on these topics. He said that for a residual set of continuous functions, these each has only a unique maximizing measure. That is, this set is a singleton. Furthermore, Morris showed that this residual set is also prevalent in the sense of Hunt-York accession. I first take a few minutes to review the definition of prevalent. Prevalent means we first give the definition of psi. Psi means for finite dimensional space, it means the big measure zero. As we know, there are no such Lebesgue measure in infinite dimensional spaces because there is uh, no non-trivial uh, shift invariant and full support measures in infinite dimensional spaces. So if we want to say something is Lebesgue measure zero, we replace it by psi in infinite dimensional spaces. What is psi? It means that for any given, we see X is topological vector space, Z is a certain subset of X, and I would say A is a subset of X A is a psi in Z if for value Z every point and we choose every delta and every neighborhood of Z in some sense, there is um, a Borel measure satisfies it is supported on X and it is compactly supported and the support contain a certain neighborhood of the point you selected or it also depends on the dirt and the neighborhood you selected. Moreover, the any shift of the set A is with respect the measure mu is 0. And we say something is prevalent if the complement is shy in the whole set. Okay, and a main conjecture on ergodic optimization is that when the system is chaotic, then the maximizing measure of typical potentials have a low complexity. To be accurate, Yuan Hunt posed an open question of typical periodic optimization. This TPO conjectures that typically potential are uniquely supported on periodic orbits. Here, chaotic usually in dynamical systems we mean uniformly hyperbolic systems or some uniformly expanding maps. Potential is the Lipschitz potentials. The first step towards TPO is made by Loeb's accession, the first attempt towards TPO. And they consider smooth orientation preserving uniformly expanding map of the circle, and the potential is the Holder continuous. They show certain TPO uh, problems. And in 2001, they consider Borch consider shift of finite type and then a small type of a small class of uh, functions called water functions at the potential. And again, full shaped and certain super continuous functions. In 2008, Mario solved this TPO for expanding dynamical systems. The the setting is also the expanding map on the circle, and the potential is the ellipsis functions. And recently, Gao and Shen considered the lower lower complexity of the maximized measures for real analytic expanding circles, and the potential are also smoother, that is, real analytic potentials. So finally, in 2019, TPO is sold by Huang, Zhang, Lian, Ma, Xu. They sold for the system for unsolved diffeomorphisms, XMA systems with holder ellipses or C1 percentiles. Verandas also consider the weak hyperbolicity. For example, singular hyperbolic flows, geometric Lorentz attractors, and for continuous potentials, they show that typically unique maximizing matter has full support and zero entropy, and also consider TPO for holder continuous potentials for this weak form of hyperbolicity. And for even weaker hyperbolicity or remove the hyperbolicity, which is made by Yang and Zhang. They consider certain surface diffeomorphisms and homeomorphisms, or diffeomorphisms away from homoclinic tendencies and with continuous potentials. They they show that this maximating matter has zero entropy. So recently, Huang Lianlu consider certain random hyperbolic systems. This is on each fiber it is anosoph and it is topological mixing on fibers. They show that the random periodic point is dense and the random periodic imaginary dense, and it got weak version of random Levesque theorems. So let me recall the definition of random dynamical systems. For random dynamical systems, we randomly choose each map and take iteration. That is, this kind of dynamical systems is called random dynamical systems. We can say phi is a measurable map from the product space to X. Then omega is replaced as the randomness, and the map is the random map we denoted by phi of omega. If the phi of omega is ck, we call it a smooth random dynamical systems. This random dynamic system is driven by a deterministic dynamic systems on omega, and we can consider the square product of a random dynamic system. It is classical deterministic dynamic systems on the product space. We also consider the random continuous functions. For random continuous functions mean functions on omega times x, and when fixed omega on each fiber, it is continuous, and the maximizing norm of each fiber is integrable with respect to p. Then we call this kind of functions random continuous functions, and we under certain quotation, then it is a Banach space. So we can contain the average of the or fix and random continuous function. I'm gonna take Sn, the first n orbit of a point and the iteration of phi. Then we define the regular site on each fiber. That is, this Birkhoff limit exists. We call beta omega is that fix an omega, the Birkhoff limit exists, and we take the supreme with respect to the regular point. We also can first take a limit sup of this kind of a Birkhoff limit, and then take supreme over x. The second way is to we take a maximum with respect to Sn over f, then take average over n and take limit sup. We call it delta omega. First, we can show that beta gamma delta is measurable with respect to delta and integrable with respect to p. So we can define beta f, gamma f, and delta f. We introduce some notations. This notation is all probability measures on the product space and with marginal p, and or we denote by MP5 be the set of all event measures with respect to phi. And alpha f is the supreme of the integral of the randomly continuous function with respect to the phi event measures. Our first result is that we found that we take average, take supreme in different steps, but we get the similar quantities. That is alpha, beta, gamma, delta, all equal to each other. And then we call this any measure is called F maximizing if they obtain this supreme. Similar to the deterministic case, we denote M max F, the set of all F maximizing measures. For random dynamic systems, the structure of the maximizing measures is that it is non-empty and complex manageable simplex, and the extreme point is ergodic, and there is at least one ergodic F maximizing measures. And we found that we let OE the site of all random continuous functions which has only one F maximizing measures. It is dense in the whole set of random continuous functions. This is the first dense result with respect to the random continuous functions for any given continuous random dynamic systems. Similar result holds for if X is a CR manifold, then it is also typical in this random holder, or each has a unique maximizing measure. Next result contains the ergodic measure, which can uniquely maximizing. Therefore, any ergodic measure, there is a random continuous function that is uniquely maximizing. We'll next result on the fully supported of the maximizing measure. First, I need to introduce random periodic orbit. First, we need to introduce a random point, means a measurable map from omega to x to probability space omega to x. That set is, we can call it the random point. And then we for each measurable map from omega to x, we consider its graph. And n graphs is called random period point with period n if it is a period invariant site under the screw product phi. So each graph is called a random period point of phi. And we take a random point G, we can define mu G that as follows. For each measurable map omega times in omega times x, we consider each fiber which has g omega. Then we take we measure such kind of omegas with respect to P. Then this measure is called mu G, introduced by random point, which is a generation of the Dirac measure for the deterministic systems. So we can give the definition of a random periodic measure, and the measure is called random periodic measure if it is there is a random orbit space, and the mu is like this. We take average of this random Dirac measure for this random point or uh, random period orbit and take a average. If omega, now we need, since we need to deal with the fully supported, we now assume omega is a compact metric space, and C, omega times S, is a set of continuous functions in the Euler sense. And we need condition A for any compact imaginary set in this product space, and mu is a invariant measure whose both is contained in A. We can find the second of a periodic measure mu n, but this support is disjoint from A, but they converge to mu in the weak start topology or narrow topology. Okay, assume find the random dimensions satisfy this condition A, then the site of maximized measure has full support is a typical subset. And for typical random uh, continuous functions, there will exist an unique maximizing measure and has full support. There is a example to show certain random hyperbolic systems satisfies condition A. For random hyperbolic systems or anisotropic systems, we consider for each fiber it a deterministic uh, hyperbolic space. The ratio of hyperbolic ratio lambda 0 is a deterministic constant on each fiber. And in this setting, we lose control of this omega section. So if omega is a differential manifold, state is a diffeomorphisms, and the expansion is weaker than E2 lambda 0, and the contraction is weaker than E2 minus lambda 0, then this system is actually a partially hyperbolic systems. So in order to get a certain random orbit, we need the topological mixing on the fibers. Means on each fibers, this the open set and the iteration will meet any open set in any fiber. And this sighting, they can show that this for random anisotropic and topological mixing of fibers, then the all periodic invariant measures extends in all the invariant measures. So for these systems, we can show that for generic continuous functions on the product uh, space has a unique maximizing measure, and it is fully supported. That is, it satisfies condition A. Next, we consider the zero temperature limits. we need to introduce random expansiveness. Means these I need two different point. These their orbit will departure at a certain distance. We call this random variable distance epsilon zero, and we can define a separating site with respect to the random variable epsilon, and we can introduce strong expansiveness, satisfy this condition. Okay, we have also introduced the specification conditions for random dynamic systems. Means for different, if there is an for each C, and there will be an unvalued random variable L, and for each we can take for each K points, and integers like this, if the gap of the sequence satisfies this condition bounded by from below by the LC, and we can find a point is true orbit, and can shadow this segment of orbit. We call this kind of with K specification, and if LC is independent of K, we call phi satisfies specification. Okay, we can define similar quantities like topological pressures, and as usual way, I don't want to see the details. And we can get the variational principles for random dynamic systems, and the topological pressure equal to supreme of the uh, convolutional uh, entropy plus the integral of F. Yes, yes. And take a supreme with respect to the all the invert measures. And the measure which makes the supreme hold, we call it equilibrium state. We can also define certain Gibbs states using some details on the omega conjugate, and two conjugate of a set, and the process definition of Gibbs state. We To get uniqueness of equilibrium states, we need expansiveness, specification, and also Bowen sample conditions. So this set is KV is a certain random version of Bowen summable conditions. Okay, when the system is strongly expansive and satisfies one specification, then for each F, there will be a unique Gibbs state, and it is environment and ergodic. If further, this potential falls in the class of the Bowen summable conditions, then these Gibbs states also serves as the unique equilibrium states for F. So we can summarize our final result here about zero temperature limits, another criterion of the maximizing measure. So under the above conditions, that is expansive is the specification and Bowen sample conditions, these three conditions carry that for each T, and there will be an unique Gibbs equilibrium states we call it mu TF, and M infinity will be the accumulated point at infinity of mu TF. Then mu infinity is a maximizing measure of F. And the following things hold. The column C9 metric entropy of mu infinity equals to the following things. In particular, it equals to the theorem of the Ks metric entropy with respect to all the maximizing measure. Okay, this is the our last result about the okay, we can our recent work we also considering algorithmic optimization for random correspondence or set valued map. And our second result is on prevalence of the uniqueness of F maximizing measures. For the first two, we almost finished. The following two is ongoing one. The first, we also want to weaker forms of hyperbolicity. And if this maximizing measure has lower complexity, so whether it have zero entropy, etc. And the fourth, in my opinion, is more interesting, is large deviation of maximizing measures. For both deterministic dynamic systems or random dynamic systems. Okay, that's all. Thanks.
Thank you very much, Professor Lee.
Sorry, I'm late for about
Yes,
5 minutes.
that's okay. Yes. Now, there is not much time for taking many questions. Is there any quick question from the audience? If there are no questions, let us thank the speaker again.
Thanks.
Our next talk will start in 1 minute.